This is the Chemical Quantities and Calculations screencast. This is actually part 1 of 3, which covers atomic mass units and moles. Please print and have your Chemical Quantities and Calculations handout available. The handout is available in the Documents section of Sakai and is very useful to take notes with and use for a study guide, solving problems, and for the quiz. Please also have a periodic table of elements available. Atomic mass units are very straightforward. An atomic mass unit is defined as a single atom, hence atomic mass, and it's actually defined as 1/12 the mass of a carbon-12 isotope. Carbon-12 isotope has 6 protons, 6 neutrons, and one of those single protons is 1/12 of this entire mass, hence the definition. So, carbon-12 by definition is exactly 12 AMU, and the element carbon, as defined in the periodic table, is 12.01 AMUs, which is also equal to 12.01 grams per mole because of how we define moles and grams and using Avogadro's number. So the conversion here is 1 AMU is 1 gram per mole, and a proton always has a mass of approximately 1 AMU. The atomic weights vary because there's different numbers of protons in the elements. And then 1 gram is approximately equal to 606 trillion AMU. So we use the grams in the macroscopic world, and then we use the protons and the AMUs in the microscopic world, so we can convert between the two. And that's why we use moles. 1 mole is 6.022 times 10 to the 23 atoms, and it allows us to go from the macroscopic world to the microscopic world. Atomic mass factors are useful for calculating numbers of atoms and masses of atoms. And the way they're used is the way we define atoms and their atomic weights. So 1 phosphorus atom weighs 30.97 AMU. It can be written as 1 atom divided by 30.97 AMU, or the inverse. So when we ask what is the mass in AMU of 75 p atoms, or phosphorus atoms, that just means we want to take the number of atoms and multiply it by a conversion factor to get AMU. That's the mass. So 75 p atoms times 30.97 divided by 1 p atom yields 2,323 AMU. We can also calculate how many copper atoms have a mass of 4.5 times 10 to the 5 by just taking 4.5 times 10 to the 5 AMU and multiplying it by the conversion factor, which is just determined by simply pulling out the periodic table of elements, looking up copper, and writing this conversion factor. And then you get the number of copper atoms. To go to formula mass calculations, let's take a look at Na2SO4. And Na2SO4 is just simply sodium sulfate, and you can see that from your periodic chart of ions. This happens to be a polyatomic ion bonding with sodium. So let's look at the formula here, and this formula says, based on these subscripts, and a 1 is assumed for the subscript of sulfur, there are 2 atoms of sodium, 1 atom of sulfur, and then 4 atoms of oxygen for every molecule of Na2SO4. So we take a look at the masses and we multiply them by the number of atoms. So there's 2 atoms of sodium, 1 atom of sulfur, 4 atoms of oxygen, multiply them by the AMUs per atom, and we get atomic mass units. We sum these units up, and we get a formula mass of Na2SO4, which is 142.05 AMU, and this is very similar to some of the weighted average problems you've solved previously. The mole, as defined, is equal to Avogadro's number, which is 6.022 times 10 to the 23 items. You need to memorize this. You use it enough that you should memorize it. And it's an exact number of items. The items could be anything, such as, in chemistry, atoms or molecules. It could also be grains of sand on a beach. The mole can be written as an equality, and MOL is just an abbreviation for mole, just like IN is an abbreviation for inch. So 1 mole is equal to 6.022 times 10 to the 23 items. Here's an example of a mole of carbon is 6.022 times 10 to the 23 atoms of carbon. And there's another example for sodium. And then a mole of water, which is H2O, is 6.022 times 10 to the 23 molecules of water. The same can be said of carbon dioxide, and it's molecules of carbon dioxide. And here's how the mole can be written as a conversion factor. And the conversion factor, of course, is useful while performing dimensional analysis and solving problems. So let's do a calculation here. Right here it says calculation, and that's what we're going to do. And then there's always a subject heading here. How many moles of CO2 are 2.50 times 10 to the 24 CO2 molecules? We simply write down the molecules. We know 1 mole of CO2 is 6.022 times 10 to the 23 molecules. If you understand this definition right here, a mole of CO2 is Avogadro's number of molecules. You multiply those out and you get a quick and dirty answer of 4.15 moles of CO2. Very straightforward problem if you understand what they are asking. Let's look at molecular formula from subscripts. Formula is a relationship of atoms. And it also defines the moles of each element in 1 mole of compound. So, 1 molecule of C6H12O6 is 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen, and these can also be represented in moles. So let's ask how many oxygen atoms are in 0.150 moles of aspirin. You have a mole of this substance. You know that within this substance, because of the formula, there are 4 moles of oxygen. That's what that subscript means. If you can recognize that factor, this problem becomes extremely straightforward to solve. You take the moles of aspirin. You know that 4 moles of oxygen occur in every mole of aspirin, and then you multiply it by the number of atoms in a mole. All your units cancel, and you get 6.31 times 10 to the 23 oxygen atoms. So first you're going to convert the aspirin moles, the quantities, to moles of oxygen, and then from moles of oxygen you're going to convert it to atoms of oxygen. And that's done with Avogadro's number. Thank you for watching this screencast.